Hi everyone, I'm Peter. I think we only have Peter in the chat, right?
No, we have a few attendees.
Okay,
7 attendees.
that's nice. Yes, my name is Viktor, and I work very much with Elias. I was also tasked to do these tests, but I work with communication links and not networks. And what I wanted to present today is just like the type of topic I'm pursuing, what my goals are, what I'm working on right now, and I'm also going to show some of the method I'm using to kind of get some answers of what works, what doesn't work in the underwater channel for communication. And I'm also going to show some preliminary results. I'm not going to go through the method I'm using because it's not finished yet, but I have at least some nice results to show. So my focus is to work with basically a family of methods that they have some properties that make them overall more robust than other families of communication methods. So I want to stay within this family so that I have a base level robustness in all the methods that I develop. And I'm in particularly focusing on shallow channels because that's where this is, I think, mostly applicable. You have a lot of time variability, large surface, not as applicable to maybe under ice conditions where everything is standing still. And yeah, so you know, the underwater channel has very many phases, and you can't really, no method will be able to take all of them. Unfortunately. But what I also want to do is to be able to scale up the bit rate and still be within this family of methods. So that's one point that I'm looking at right now. And I'm also very careful with the bandwidth. You know, sometimes when you see, you know, this modem has this many bits per second, and you're saying, wow, that sounds very nice. But then you look at the bandwidth, and they're using an enormous amount of bandwidth. So there's always a trade-off with bandwidth and bit rate. But I'm a bit. I like to focus on smaller bandwidths, or you know, not just like wow, big bit rate and big bandwidth. But because also a good thing there is that if you're careful with the bandwidth, you make things work nice. You have a decent bit rate. You can put in more users, and in real life that's very important for like a real application. And I also want to make a method that I want to look at all the necessary steps for a communication link. There are many different steps that you need to fix, many different research problems, and usually when you publish something, you go on one of them at a time. It's not always that you present the entire method in a paper, but I'm trying to go through all the problems one by one and making sure that I have something at the end that will actually be implementable. And then one last thing that I'm interested in is to have an adaptable method. And now this sounds a bit maybe vague, but it's kind of like what Elias was after, where the network, if you're in a condition where you can lower the power, you do so, and you save a lot of other resources instead. I like the idea that the link scales both the length of the data, so not all data packages are the same length. You scale it to what you need to send, so you are conservative with the time resource. Yeah, and all other things you can, so that you could like scale robustness depending on if you're on a good channel, bad channel, and like how fast the method is. So right now I'm working on a method to try and increase the highest bitrate you can get with like a textbook robust method. And yeah, I'm gonna say which one I mean in the next slide. But still keeping an okay robustness. So you always lose some robustness when you increase the bitrate. There's like a standard trade-off there. But it's good to have the possibility to go up in bitrate when you can live with the lower robustness. And in the future, I need to look at synchronization and detection of the package. That's a problem in of itself, to know when has a signal arrived, where did it start in time, because that's usually another method from the data carrying method. And if you have two methods, then you're going to be limited by whichever one of them is the least reliable. So it's a very important problem to deal with. And then I am a bit interested in the setup where you have adaptable messages, like I mentioned. So you have one standard short header message that contains some network information, but also specifies another longer message afterwards, or it might not be a message afterwards, but it can be a longer data message afterwards that has another method with much higher bit rate. In general, when you have a longer data packet, you can have a code that gets better with the longer the data is in one encoded chunk. So it's part of this idea of actually being conservative with the resources you have and use what you need. And there's another thing, is that the channel underwater is very time variant. So it can have, on sinusoids, it can have this effect that you lose correlation between what you sent and what you receive. And that looks like you get a lower SMaRC, because you get less output when you correlate them. So you get a lower energy output from whatever detector you're using. So I would like to look at some waveforms that don't use sinusoids that could maybe fix this problem. Just to kind of point what type of methods we're talking about, the class of method that I'm mostly interested in are called frequency shift keying methods. And here I'm showing basically a picture of a textbook FSK. You have 4 available frequencies. You transmit the information by transmitting on one tone at a time. So depending on which one you sent, you know that they signify some bit that you have said, this tone means these 2 bits, this one means those 2, and so on. And even though this one is simple, it's actually still very useful in the underwater channel. It's like a really old textbook example, but the one property it has that makes it still useful. I mean, this MFSK is robust in general, but the information, basically the bit rate per hertz of bandwidth you have available, it has a function of log2m/m for this type of method. So if you have m equals 4, then you get one half bit per hertz of bandwidth you can use. This is why I mentioned the bandwidth in the beginning, because it's very important to the bit rate. But if you go higher, so you have more available tones and you send on one at a time, then this log2m/m, it goes down very fast, and the method becomes very, very slow in bit rate. But 4FSK is the fastest one for FSK, so that's why it's still interesting and still being used. Since it's so well known, many people have used this actually. I use it for reference, and I'm going to have it in the plots in the next slide. And another thing that I've been looking at previously is a kind of new type of error correcting code called polar code. They are a little bit hype right now. They're in the 5G standard, for example, but they're fairly new, 2009. I haven't seen very many papers using it in the underwater channel, but I know from my experience it has very good performance, like good enough that it is. I don't see any reason to do another code right now, at least. So basically, these 2 is something I used in a paper at UCOM's 2020. These 2 together. What's the time? So another, if this is the same issue that Elias has, and I have it too, to some extent. Normally, when people publish results of a method they've tried for underwater communication, you know, they go out and they try their own method. Maybe they have a reference method with it, but everyone does their own field tests at their own site, at their own time of the year, you know. And there are so many different underwater channels that you get more or less a random channel each time you go, and you don't know which one you're going to get beforehand. So when you read a lot of papers, many different methods, it's very difficult to compare and see what method is best, which one fits what I need. You just see a lot of methods, everyone gets, you know, good results, otherwise you wouldn't publish it. But how do you actually compare it? It's really difficult to make a meaningful comparison. It's, at least that's what I think personally. So there's another way to go about this, and that is to use recorded underwater channels. So someone has gone out, they've transmitted a signal to make a recording of the channel at that point in time. And then they use that instead to simulate their method or test the method. Because then they can publish the channel so everyone can use it and everyone can test their method on the exact same channel. And it's still the same problem that you only get like one, you take an axe to the number of channels that are available. You take out one here, one there, and one there. But at least you can compare. That tells you a lot more than just seeing a lot of successful field tests. So there is one available. It's called Watermark, and it's published by the Norwegian FFI. It's the Norwegian equivalent of our FY. And they have 5 recorded channels from different places. And yeah, so the recordings they made is that they've recorded, for the 5 different channels, they have recorded one impulse response every 32 to 128 milliseconds. So they make a recording, make another recording like 100 milliseconds later, and so on. And then they do this repeatedly for between 30 and 60 seconds. And that is like the channel for a 30-second period. And then so they have repeated this measurement 1 to 60 times, depending on which one you use. So for example, if I run a simulation with one of these channels, I might get 30 minutes of sound, of data, like my method going through 30 minutes of data. Yeah, and the good thing is that you can, they have published what should you say each time you use this method in your publication, so that if I see another publication that has used Watermark, I can just look at their plot and directly compare it to my plot, and the scaling will be the same, the definition of the noise will be the same, the channel, you know, you can just like look directly between the plots and directly compare them, which is very useful. So I've used 3 of the channels, and I wanted to show a bit what they look like. Hide this. No. Oh, can you see this, by the way? It's a little bit blurry. Yeah. So to understand these images, there are 2 axes. The x-axis is delay, and the y-axis is time. So the color is basically the impulse response in this direction. So, I mean, the way the impulse response, how to interpret it, is that basically where you have a very bright spot is where you have a very strong strong copy of your signal starting from that point in time. And if you have, basically if you have 2 strong colors, that means that you have 2 copies of your signal arriving 2 times with that time delay. So what you see on the x-axis is basically like the continuous copies of your signal arriving after some strong arrival. Do you understand what I mean here? Or yes? So, for example, in this one, you can see that it looks like there is one fairly strong arrival at 2 milliseconds, and it doesn't change very much over time. You have some echoes here. It's a bit difficult to see, but you can see in the color here that you have echoes, and the structure of the echoes changes over time. So this is the time variation of the channel, that the channel is changing while you're using it. And the way they've implemented this in Watermark is that it has like a continuous filter that changes the coefficients by interpolating between the different like discrete measurements that they have. Because they only have one measurement every 100 milliseconds. So when you're convolving your signal, you have to like interpolate the taps in the filter. So this channel, you can see it has two very strong contributions. It changes a bit over time. I tried to kind of circumvent the problem of detecting where the signal starts by looking at these and saying, okay, for this channel, there's a strong tap at like 4 milliseconds. So every time you decode, start at 4 milliseconds and take the signal from there. And that's not to confuse with like a synchronization method. So this one has two taps. So it actually has one reflection arriving before the main signal. This one has a main tap. It's called VCH1. And then the third one, I don't know if you can see this, but there is not really a clear main arrival here, and it's like, yeah, I don't know what to call it. Speckle. Yeah, it's like speckles. So this signal, it's more like a continuous like swath of energy coming in like some discrete places, and sometimes basically not at all. Here it's very dark blue, so basically there's no signal coming through here, more or less. It just gets destroyed. So they are very different in difficulty, these channels, like how much they destroy your signal. My experience is that this first one, NOF1, is like an easy channel, and then these other two are more like difficult channels. Yeah, I only have one slide left.
Yes. Your slot is until 2:20.
Okay. Oh, well. Right. I didn't manage to go out and scroll. Sorry? Yeah. Okay. Yeah, so here it's basically two sets of methods. One is this textbook for FSK. It's the so remember, it's the highest bitrate you can get with this robust class of methods normally, at least in the context of FSK, it's the fastest you can go. And the four channels have different markings, and then the full line is the FSK. So it's basically these three, one for each channel. On the y-axis, I have frame error rate, or packet error rate, or block error rate, whatever you want to call it. Like, what's the probability of having at least one error in the entire frame of data that you send? And on the x-axis, it's SMaRC. And the numbers here might not say very much. You have to compare it to another method to kind of get some idea like what the actual numbers here. So let's not focus too much on them. So these dashed lines, I have one for each channel here as well. And it's the new method that I'm working on. And of course, if you compare these 2 by 2, so for example, this blue one, full line with this dashed one, you have something like, it's like 2 dB worse performance in terms of error probability. So it is less robust, but it's supposed to be less robust. Like you can't really have both at the same time. And then these two are comparable, these two, and then these two are comparable. And if you look at this one, it looks like it's leveling out at 10 to the power minus, so like having an error rate of 1/1000. And it's not going to get better when the SNR goes up. And that's because the channel itself has a limit on how good the method can perform. So even though you reduce the noise that you add on, like the noise from the method itself, like the reverberation and other things, kind of make it plan out. But the big difference, and this is where the one I'm working on is a bit interesting. If you compare these first two, the easy channel called NOF1, the FSK version has 226 bits per second, and it takes about 2 seconds to transmit the frame. And the new one, it can go up to like 700 bits per second, and it takes 0.3 seconds to send it, because the time slot is important as well, so you don't have network collisions. And again, I'm only using 4 kHz bandwidth, so it's not so much bandwidth. So 700 is very high compared to the bandwidth. But then to have some useful results from the other ones, or like how you have to scale up the robustness of them to make them actually usable, they have like 400 bits per second, and then the other one has 200. But it's still twice that of the other one. So the conclusion is basically what method you use depends on where you are, or what the situation you are in, and that's why I'm interested in this adaptability of the link, because both of them are useful. But if you are the good thing here is that if you are in a channel that is a bit easier, nicer, with this method you have the possibility to scale up the bit rate to get it a lot higher, which you wouldn't be able to do if you stayed within the robust class of methods, or within the FSK class of methods. Yeah, and that was all I wanted to say about that. So thank you for listening.